transducer only converts that information. Sometimes both will be used as a pressure transducer or something. This kind of words will be used, but don't get confused. You can use whenever it is possible sensor and possible transducer. So basically, we are going to discuss about what does that sensor means and how it is a typically structure of it. What are the building blocks of the sensors and transducers? We are going to discuss about static and dynamic characteristics of this, and we may be having covering some of the parts like what is displacement sensor, what is its basic principle, position, proximity, all these stuffs. Okay. So this last time we had a discussion. We are now concentrating on this part, that is sensor. Because you learn in mechatronics, you should have a knowledge of all the blocks. These are the blocks which we are going to. That's what I'm putting this PPT all the time in first slide itself. Okay, so we are now discussing about the sensors part. So here we are having a sensors. Okay, sensor is nothing but which is measuring typical parameters, or maybe knowing what is the status of my system, what is the basically temperature, pressure is there, maybe position, speed, so many parameters you can sense it. So we are going to, this is nothing but input is nothing but a certain parameter, and that parameter is to be converted into electrical quantity. Electrical quantity means maybe you're going to convert in terms of a voltage, also maybe converting into current. Okay, these are the output I expect as it is. But sometimes if I look into the strain gauge of the strain gauge type of a sensor, so what we are going to do is we are going to give an input that will change the resistance, and that change in the resistance is again converted into the voltage. So that is also we are going to do it. But ultimately, you want the information of this particular parameter in terms of a voltage, either voltage or in terms of a current. So because voltage is sensed by your microcontroller, current also needed. The reason for this is typically that is 420 milliamperes type of an output is most of the time it is there on the sensors. Is there is and how it is to be converted again voltage. That part also we are going to discuss into this. So basically, if I look into the any kind of a system is nothing but a black box or kind of a device which will take an inputs and generates an output. And when it is going to convert that input into output, it involves its environment, its system boundaries, so many stuff into this. Okay, like an electric motor, you can a simple example, electrical energy. That energy in terms of a voltage and current, we are going to send it into this electric motor, and it will convert that electrical energy into a mechanical energy. And mechanical energy means ultimately you're going to convert into the torque and omega as an output parameters for this. So when you are going to do a measurement, okay, so we are using the same concept. Okay, system may be actuator as in one of the system, control system itself is in one system, and like this. So same is there with the measurement system. So in measurement system, we are having a certain physical phenomena it is going to happen, like in a temperature, the body is increasing like this. I want to know that temperature value in terms of a voltage or current. So I need a certain mechanism inside it. And that is what it is called as a sensory system or sensor system. Okay. So when we are going to do this, there is some kind of a loss or some kind of here that is what a measurement error comes into this. How much amount of error I can tolerate, what is my perfect design, and that all comes into this. Okay. So when we look into the measurement system, how it works, basically it starts with certain blocks. It passes the information in certain blocks. First of all, variable to sense. I can take I want to sense either I will say it is in a force or something. Okay, just take an example. This is my cantilever beam. Okay, and I want to know how much amount of force I applied at this location. Okay, so what I can do, this is my basically physical phenomena, and I need to have a certain mechanism which will convert force into certain electrical quantity. Okay, electrical quantity. And how can I convert? And that is what in a mechanism. That is what in a mechanism. So you need to convert that force into an electrical quantity. Maybe I am using a strain gauge principle. That is what in a basic principle of this. So it involves certain principle. What does that principle says? Principle says means if I apply a force onto any component, okay, this is my input, that's what I am taking on x-axis, and output will be in a resistance change. That is what a change in the resistance. I can observe this kind of in a graph, I can observe it. And what are this constant is nothing but my slope. Okay, this is what I can observe it. So this slope is nothing but a gain or how much amount of gain, how come is there. That is what it is told by this graph. If my graph is somewhere like this, it was in a lesser sensitivity. If it is more sensitive means I have another this graph. So sensitivity increases in this direction. Okay. So how can I do this? That is what in a basic principle means. If I take on a bar or kind of any structure, okay, and if I apply the force onto this, okay, I may be applying a tensile force. So what are going to reduce and length is going to increase, okay, with certain amount delta L. And due to this change in the delta L and reduction in the area, so resistance of this electrical quantity, electrical parameter of this particular bar is going to change. And that is what it is called as a resistivity. Okay. So now I am taking an advantage of this particular principle and I want to convert that as a sensor. So once I got a change in the resistance, this is I got a change in the resistance. Resistance need to be converted into electrical signal. That may be on a voltage I want to convert. Okay. So how can I do it? I can now have, I know the potentiometer as in a basic principle. Whenever I'm going to have voltage, I'm going to apply here 0, maybe in some volt. And this is what on a point I can measure the voltage across these 2 points. And whenever I'm going to have a change in the position of this, I can say that out voltage. And that is what on a potentiometric principle. Another principle are my delta V. So there will be a potentiometric circuit, okay, or rheostat type of circuit can be used. Another one, I can have a Wheatstone bridge as a circuit, we can use it. And that is what the way you can have a mechanism which will convert your delta R, or first you have a force to change in the resistance, change in the resistance to change in the voltage. And this is nothing but my electrical signal. This is what an electrical signal I have. Now this signal put this particular force information into changing the resistance and changing the resistance into delta V, and it is may have a certain kind of a noise it will capture, may have a certain kind of a loss in the information, and that's what we need in a certain process. That is what an addition or reduction of the removal of the noise or something, and that is what as it is called as a signal processor. It means if my varying quantity like this is what it is varying. Here I may have a change in the resistance in this fashion. This may happen due to interference of the external environment. And this also voltage may have something like more variation like this. Okay, so here it is in a smooth variation. Here it is some noise has captured. Again, some more noise has captured. So to remove this, whatever the noise it has captured, okay, that is basically a process called is a signal processing. And either we can record it or transmit it or display on the digital indicator or kind of things we can do it. So that is what basically a concept of measurement system. Okay. And here, whenever we are going to use in a concept of measurement, means I have to have this resistivity principle of material. Any material I can take it, I can observe different materials and I can identify which is the best suited for this. And that is what the way that sensory systems. So basically in instrumentation, so term transducer is also used in relation to the measurement system. So this is what it is defined, which converts a change in some physical variable into related change in some other physical variable. That is what it's called as a transducer. Sometimes you can say sensor can be a transducer. However, measurement system may use a transducers in addition to the sensors. But that is for conversion purpose. Okay. Apply the measure system measurement. My input is pressure, output is value of the pressure or indicator, which is maybe a pressure sensor. You might be knowing this is my dial and I'm going to have a high pressure gas here. This dial is now showing a marker and this is my initial pressure and I can have this change in the pressure. This position of the dial is going to tell me the information how much amount of pressure is there. Means water, this page P is a converted in angle. The same way, if I connect this at a kind of electrical quantity or something, I will get a delta V as a change, electrical signal. I may get maybe in a pressure sensors like in a U2 manometer or something. Okay, this tube is connected to somewhere else and this is what I can now sense this height. Okay, and this is what on a displacement also I can measure it like this. If you look into the speed measurement, input is my change, that is what pulses of the signal or speed of this, and output will be in a value, maybe in a mechanical counter I can use it, maybe a electrical signal I can use it. Also in case of a flow rate, I'm going to get the flow value in mechanical motion. Maybe in a mechanical motion means you might be remembering there was mm, rotameter. After the rotameter, there is a sensor which is rotating within that particular speed. And that is what my rotameter is taking in a position of that floater and kind of this. And that whole stuff can be further converted into electrical signal. That is what in a flow rate measurement system. Nowadays, that ultrasonic sensors also comes. And they are also doing the same stuff and doing this. Okay. When I look into the measurement, measuring system altogether, okay. In this measuring system, you can look at the input to pressure, degree of hotness or coldness. Okay, and that is converted into output like an EMF, change in the electromotive force it is called, or it is simply represented into change in the voltage. That's it. Okay, so that is what basically a sensor. Signal processing means here I can connect with so this is this I can connect in terms of a MAX 6675 sensor for the thermocouple, which is very low voltage change will be converted into high voltage. This is going to an amplifying kind of thing. Also, it is used to remove the unnecessary signals and all this stuff. If I use a strain gauge as a sensor instead of thermocouple, I can use a Wheatstone bridge, amplifier, all this comes under the signal processing. Along with that, we are also working with filters, okay, for signal processing purpose. Okay, then we can have a display, record, and transmit kind of stuff. You can do. Okay, that is our representation. Okay. These are the basically building blocks for this. Okay, what is going to happen in the typically RTD type of transducer, that is a resistance temperature detector. Okay, temperature is my signal. I'm going to change that change in the temperature. Certain materials like in a Peltier or kind of that certain materials are there. Okay, if I'm going to have an input as in a temperature, outcomes, I may observe such type of curve. Okay, as temperature increases, my resistance is going to change, and that is what basically mechanism or a basic principle used in this particular sensor. Okay, I can have a temperature. I can just put up on a bed. I can now convert it that information of the temperature into change in the resistance, and this change in the resistance can be Wheatstone bridge, potentiometer, or something which will cause a change in the current, either current or voltage, whichever it is possible. And then that is the way it makes. Okay. Now we'll look at what will be the characteristics of characteristics means its behavior. I can now just complete this word characteristics means I want to know the behavior, how it behaves. When I'm given under what condition means if I have a sensor, I put upon some input to this, how change is going to happen, how it is going to interfere with another environment. All this stuff you need to identify, and that is what it is called as characteristics. And these characteristics may be two ways. One is static, another is in a dynamic. Static means already we had in a discussion. What does that static means? Static means whenever I'm going to create any change into my system, the change I'm going to do is its frequency of the change or whatever the speed of the change in the particular parameter is very low compared to its natural frequency. That is what it is called again. I can just show you one thing. Here already we have seen magnification factor curve. That is omega is my forcing frequency. This is my omega n natural frequency. This is my output. Okay, I am having this particular variation. If I provide a more damping, I can get this way. But during this particular range, my system is not showing much change compared to my as even though I'm increasing the frequency. Means if my system is this is my system. Okay, this is sensor system or something. I'm giving some input to this and I'm observing output. I'm going to give an input like just like with respect to time. I'm giving a change in the temperature or something. Okay, I have a small change like this, and then it is remaining constant. Then it is going to happen. So my sensor will get a sufficient time to settle down what are the oscillations, and then I'm getting some kind of nonsense. What are this variation due to excitation of its natural processes? Okay, but if my temperature variation is very fast, just check this is going to happen. My sensor may not behave this way, but may behave in something different fashion. This is what in a dynamic condition comes. Because if you observe the variation of this, omega is very high compared in this case. And here it's a frequency or omega, I can say, frequency of change or whatever it is low. So this becomes in a static characteristics and this becomes in a dynamic characteristics. If my system is beyond this particular, it is called as a dynamic characteristics. Means I need to take account of change in the frequency, not omega, I will say, change in the frequency. And here I need not to worry about it. And then it is called as a static part of it. Okay. We'll now look at a certain parameters which says about static characteristics. So accuracy error, I'm not going to give a more detail or not on this. Accuracy and error, there will be a true value and your sensor is not sensing that much exactly. Difference between accuracy and error means difference of these two. True value, maybe I'm going to measure a distance like 10 mm distance is there. Okay. And I have two sensors. This is my sensor 1 and this is my sensor 2. And I know this value is in a 10 meter fix. Okay. This distance is 10 meter. I use the sensor with this and I got 10.1 something. And I use this sensor, I got a 9.9. Okay. So this is what actually the sensor output should be 10, but this sensor is having this much deviation. Means it is showing some higher values for S1 and lower values for S2. So obviously this much is nothing but an error it is going to happen, and that error should be minimum in your any sensor, and this much error should be there when you are going to use in a sensor for particular application. So next is what is the maximum range it can cover? If you look into the RTD or some kind of a sensor, it can sense temperature up to very high degree. But if you look into the thermocouple or something, it can sense up to 500. Some sensors sense up to 500. Beyond 500, it cannot sense it. Some thermocouple can sense in a temperature up to 2000 also. Okay, so that is what is the minimum value to the maximum value. 2 is nothing but a range. Resolution means a very important stuff. There is a big difference between accuracy and resolution. Okay, resolution is nothing but in the smallest increment I can detect it. Okay, smallest increment means whenever I'm going to create any change into the parameter, what is the minimum value it can sense, and that is what it is called as a resolution for it. You can just look at the difference between this accuracy and resolution of this. So this is red color indicates my true value. Okay, and I sense my measuring system has sensed this much value. Now I can say this is my accuracy of my system. Accuracy. But my instrument can take a change in the step of much small, which is called as resolution. And that is what the way you can look into the difference in accuracy and resolution. So you can look at, there is another parameter, it is precision, okay, precise. So this is more precise, but not much accurate. Accurate means this is where I get all the values, okay. Here no precision, no accuracy, nothing you can observe it. Okay, precision without accuracy here in first feature. Second feature, without average all these numbers, I can get my value somewhere here. But precision means I'm going to do a repetitive measurement, then it comes upon a precision. Okay, and I may be using that instrument 10 times and observed. So these values are not lying to the particular value. Just take a simple example. I took a micrometer or something, micrometer screw gauge, and I'm going to measure the diameter of this pipe. Okay, and I measured this pipe diameter 10 times. Okay, and I observed 10 times this diameter is falling in this fashion. Okay, but what are this measurement is near to this, that accurate, but this, because my value should be very near to each other, and that is what it is seen in the last one, that is precision with accuracy. Another static parameter comes to the hysteresis. Hysteresis means if I'm going to measure, let's just take an example of temperature sensing. Okay, take an RTD as an input. This is my temperature and my voltage output or something. I'm going to do it. I observed as I'm going to increase the temperature, it is following this particular curve. Okay, and reach to this point. Okay, and then again I'm going to decrease the temperature smoothly, then it is going to follow this particular curve. But actually it should the same path, and it is not falling. And what are the gap of these two is called as an hysteresis. Means if I'm going in forward direction, okay, if I'm going to here, just take an example, here maybe in a 200 degrees Celsius. In forward direction, I received the voltage for 200 degrees somewhere, maybe on a 5 volt or something. And saying in reverse path, I got the voltage maybe 5.75 or something. So this gap is nothing but a big gap, and that is what it is called as due to the hysteresis, repetitive. If I'm going to go and talk how that particular sensor is going to sense it, and that is what a hysteresis error. Another one, non-linearity. Very important stuff. Non-linear systems and linear systems. When I'm going to look at a linear system and non-linear systems. I have a system, just take an example. This is my system. I'm going to give an input to this, maybe an X I'm going to give, and I'm going to have an output Y. When I'm going to plot these two, this is my X and this is my Y, I'm getting this is input, I can say, and this is my output from the system. My behavior, when I'm going to plot, I will get on a certain straight line or something. Maybe this straight line is somewhere offsetted like this or something. But all the time it is having a straight line behavior, and that is what it is called as having a slope. And I can represent x is a function of, sorry, y is a function of x in terms of a linear equation. And then I can say it is linearity. Okay, and I can now represent this into mx plus c kind of an equation, and I can find the characteristics of it. Sometimes you may have in a system like this system, this is system, this is x is my input and z is my output. And I observed this behavior is something like this. This is my x input, y is my output. This behavior is something like this. This is not straight line now. It has having some y is now function of x is a kind of a higher order polynomial, Okay. Then I need to represent y is equal to c0 plus c1x plus c2x square or something. So this is what called as a non-linear behavior. This is one way you can identify linearity and non-linearity in the system. Another one way of doing the same thing, just take an example. This is one equation that is a linear and this is non-linear. Now there is another principle is called as a superposition principle. Superposition. In superposition, what happens if they put my linear system, maybe I'm giving an x1 as an input, I'm getting y1 as an output, and I'm getting x2 as an input, y2 as an output. Now I can represent x1 plus x2 as an input to my system, and I'm getting an output y1 plus y2, then I can say it is in a linear relation. And this is what it is called as in a superposition principle. This superposition principle is out here. Okay. If this is not going to follow, if you follow this linear equation, you can observe if I have an x1 value 5 this particular steps. Okay, this is my x1, this is my x2, and I can quite easily observe this will be a y1, y2, and if I go give both the values as an x1 plus x2, I'll get the value as in y1 plus y2 or something like this. Okay, that is the way you can have a linearity principle. That is a superposition principle. Okay, another one, if I multiply this x with some constant 2 times of x, given an instrument, I'm getting output 2y something. Then also it is called as a linear, and that is what it is called as an associative principle or something. Okay, this is what in a mathematics it comes into this in most of the places. Okay, so sensors, this is what it is explained. If I have a sensor, A, input B, and output is also A plus B or something like this. Okay. And several non-linearities, why it happens, non-linear systems, why it happens non-linearity. Basically, it is due to the friction. That is what one thing. Another one, eccentricity in the mechanical system, then backlash into the mechanical system, then hysteresis. There is a problem of saturation. Saturation somewhere it will not show any kind of a value, even though you are increasing the input. That is what it's called as in saturation. And dead band means it is typically if I'm going to give some input to my system, even though it is not showing any output, and that is the region in which it is not showing any kind of an output. That is what it is called as a dead band. So most important parameter is in a sensitive. This is what in a linear way, non-linear variation of my sensor input output. Non-linear variation. I can now observe here very small change result into the that I can say delta V or delta X. If I observe here, the same amount of change I'm going to do it, but what are these values will be very low. Delta V1 or here it is delta 2. So that's what it is called as a highly sensitive region. This is what an intermediate region, and this is what in a very low sensitivity. Means simply you can observe this line is having a larger slope. This line is having a smaller slope. Okay, and if my sensor is having a smaller slope, I can say it is in a low sensitivity. And if my sensor having a large slope, where slope value is more, then I can say it is a highly sensitive sensor. Next one is a repeatability, how at my represents repeatable results, and it is related to hysteresis. Then another important part is in a backlash. Backlash means it is due to the gear. You can observe one thing into the most of the instruments like in a gearing sort of system. This is my one tape and this is my another tape. Okay, or something. I have another machine tape inside it. I cannot have what are the dimension of this tape to this much gap. Okay, the reason that I need to maintain that gap, like in a smooth operation. Due to this particular gap, okay, during this gap, your system is not changing anything. It is not showing any kind of an output, and that is what it is called as a backlash. Okay, and backlash may be in a what are the clearance in the between the teeth. This is one reason. Another, you may have a slider or something, and that there is a gap in the slider. That is also reason for the backlash and things. we can have the most important. I'm going to give an input command to my system from this. And at this point, I got up to this point, I got an output. But beyond this particular input, it is not showing me any output. And that's what this point is called as a saturation point. Like, I'm just take an example of motor. I have a motor, I given a maybe 12 volt is the maximum limit. I increase the voltage. So even it has an for 1500 RPM. Even though I'm going to pump more and more voltage inside the motor, so it is not increasing the speed. And that is what a saturation can be. And this is what it is observed in most of the sensors, also in actuators also. This is what positive side saturation. This is what negative side saturation, I can say. It is negative saturation. This other reverse way. Another one is in a dead band. In this dead band, what it happens? If I'm going to create any change between this point to this point, it is not showing any kind of an output and output here. That is what it is. Okay? It is not showing any change into this, and that's the reason it is. This is also very important because this creates a non-linearity whenever we are using a sensor or actuator. So these characteristics will be the same for actuators also. It is not to the only sensors and transducers. Okay. Then next comes upon stability of the system. Stability means I can have a stable behavior, unstable behavior, or something. I will just take on one simple example. Just take an this is my pendulum. Okay, this is a rod of the pendulum, I can say. This is my mass. So this equation can be represented as an I theta double dot plus what are the restoring force, restoring torque into theta and kind of things, this equation. Okay, I can now see, derive this equation. Okay, now if I change the position here, I will get mass m into g or something, and this force is a tensile force, tension force. That is what mg cos theta, and this force is causing mg sine theta. Okay, and this may be the length of it. Okay, I can now I into theta double dot plus mgl mg sine theta is nothing but in my restoring force, because restoring force means it is bringing this bob to this equilibrium position. This is my equilibrium position into length. That is what inertia, which now I can represent ml square because mass is concentrated at this distance. That's what I can write. And finally, I'll get the equation theta double dot g by L, okay, sine theta, which is equal to 0. Okay, this is a non-linear differential equation. It is not linear. The reason for this sine theta, if my theta is very small, okay, theta is very small means less than 1 degree or something. Sine theta is equal to approximately, I can represent theta. Okay. So I cannot have sine theta is equal to theta. Okay, that is what basically comes. Sorry. Okay, then we come up with equations. Sorry, here it is. Mg, then restoring force, tensile force, mg cos theta, and this is mg sine theta. Okay, this is my mass m, this is my length L. Here there is no restoring force it is creating, because what are the tension here, which is equal to mg. That's what, there is no restoring force at this location. But here it will be there. It's all the way creating a gravitational force here, and that's what you can write mg, sorry, ml square theta double dot plus mg sine theta into L, which is equal to 0. I can write theta double dot plus G by L sine theta, which is equal to 0. This is what an equation we got it. Okay, if my theta is very small, like it is very small, small means literally small, it is one radian that. So one less than not 1 radian, but it is very small, like theta 0 degree, 1 degree or less. Then I can say sine theta is equal to approximately theta, and I can say. So there are. So if I want to identify how many number of equilibriums for this equilibriums, I have n number of equilibriums, points, equilibriums. Reason for this, I can have one position here, and I can write an upper right position. This is also another position. So this is also one of the equilibrium. Then again it will come back and again here. Then I can have such n number of equilibriums. Means I can have 0 degree, then 180 degree, then 360 degree, and likewise I can have all these positions. Out of that, if I consider this as a point, okay, if I'm going to just take one simple example, okay, with respect to time, I'm going to plot this, okay. If my I can get an oscillations like this, okay, and if my angle is here, 360 degree or something, so it will not go and settle down your pendulum in upright position, but it will come here, this will come back here and it will oscillate here. Here it is, I may have 180 degrees Celsius, 180 degree, and may get an. This is because here I have, okay, this can be quite easily shown axis. On one axis, I'll put theta, and another axis, I'll put theta dot velocity position, and this is what on the velocity. This is my one theta. First equilibrium is theta, and zero is my equilibrium. Another one theta and theta dot. My equilibrium first second equilibrium is 180. With a triangle something. What it is called as in a stable equilibrium. And what I and that's what you need to identify stability into the system. That is the same thing in here. You can see whenever I'm going to disturb this, it will never come to this position. That's what is unstable. Okay. And if I have a round shape or some ball is there, and if I'm going to display it, oscillate, and it will get into friction. If I have a smooth or no friction, I can have a marginally stable, means it is continuously oscillating because there is no element absorb energy, and that's what it is marginally stable, it is called, because it is continually oscillating to the infinite time. And that is what the basically difference between stable system and unstable system. What we are going to do is we can simulate this on MATLAB and you can observe it. I will show you sometime in a later stage. So then next comes up in a dynamic characteristics. And first dynamic characteristics is it's a transient response. Transient response means I'm going to have this is my system. Okay. I'm going to give an input to the system. Means with respect to time, I'm suddenly changing the input to my system. What will be the output? Output will be typically a curve. This is my input and my output will be something will get oscillate and will get its step. But it happens because each and every system has its stiffness, has its mass, and has a damping into this. Okay, in mechanical domain, if I look at the same thing is with electrical, perhaps resistance, inductance, so many other stuffs will be there. And it has its own natural frequencies. That is what it is. You can represent in mechanical K by M. So obviously these natural frequencies, I will not say it is, if it is my single degree freedom system, I will get only one natural frequency. If I am a multi-degree freedom system, I may have a multiple natural frequencies. And these natural frequencies will get excited whenever I am going to have any kind of a change in the input into the system. And that is what it is called as a transient. Just you can observe one thing when you are going to have in morning you maybe want to go out with your bike or something. Pick up the vehicle. When I put up on a starter button or I will put up on a key, what is going to happen? The speed of the motor is increasing from one point to another point. Maybe initially it was 0, it is going maybe in 1,500 or something. Okay, depends on type of an engine. So as it is going to change the state, initially the speed was 0 is one state, another state is maybe in 1,500, speed is another state. So when it is going to change the state, you can observe certain vibrations and oscillations, and these oscillations will get die after certain time. And this is what it is called as a transient response. The same thing you can observe one thing. If I have a sensor system like a temperature thermocouple or something, this is my thermocouple or temperature sensor. So initially my temperature was somewhere 20 degree and suddenly it is increased to 50 degree or something. Okay. So output will not show me exactly like this, but it will have a certain oscillations and then it will come down to this. This is what the phase is called as a transient phase. And this phase is very important, and for any sensor, this transient should be very minimum. And this time should be in microsecond or millisecond. Okay. If it is more, your system may not result into the accurate measurement. That may happen. One more example, you may be knowing temperature sensor. Why the doctor is telling you to maintain that for certain period? Because it is taking some smoothly increasing the temperature and getting stabilized in somewhere here. So this much period is nothing but maybe a 2 minutes or something. And that is what thermal systems are very slow compared to mechanical systems. Okay? Mechanical to electrical systems. And electrical systems are very slow compared to any optical systems. That's what, if your sensor is working on optical principle, it will show me a faster result. It will show me an immediate change and will get stabilized. But if I say electrical system, so it is very less because light speed is somewhere 3 lakhs, 3 into 10 raised to 5 into kilometers per second. This is my speed of the light. And that works in this fashion. Electrical system works on electrical signals. Okay, that's what it is somewhat less, and mechanical system is again less than that, and then thermal systems are still less. That's what. If your sensor is optical, it will immediate change will show, but it will get stabilized easily. But in thermal system, it will take much time, maybe in a 2 minute, 3 minute, or some time. So that's what this is. What in the characteristics is called as a response. What is the response? Okay, how much time it takes to reach to 90% of maximum decided value is called as a rise time. This is what rise time. If it is going to an overshoot or something and reaching to the maximum value of this output, what is maximum and how much time it is taking, and that time is called as a peak time or something. Okay, and then due to this peak, it has gone beyond its value. So obviously there will be some kind of an oscillations, and this is what it is oscillating and getting stabilized. And this point is called as an entirely settled your all oscillations, and that's what it is called as a settling time. And overshoot, I can determine this is my steady state response. This is what, after this, there will not be any kind of an oscillations. And that's what it is called as a steady state for my system. Okay. And this is what it is in a transient state. Okay. And if my difference of this is my steady state value and this is my peak value, I reach somewhere in between, and difference is called as an overshoot. This overshoot, and you can represent that overshoot in with respect to steady state, how much amount of percentage variation and kind of thing you can represent. Another one, my desired value is this value, but my steady state response is going to give me this. And this is what it is called as a steady state error. This is also error in steady state domain. I will get steady state error. And that is the way you can represent any kind of transient response. You can from this transient response multiple parameters. The same, this transient response mechanical systems are not only sensory systems, actuators, or in other systems also. And this is frequency response. Frequency response means what is going to happen. Already discussed a lot of times about this. So this is my system. This is much more visible. It's a car. Okay. This is my system. I'm going to input to my system, and this is my output from the system. What I'm going to have input, I may be measuring vibrations. Imagine I'm maybe measuring vibrations. In vibrations, obviously there will be a certain oscillations. Okay, and I want to know what will be the output. This is my oscillation, output oscillation. This may be an amplitude A, I will say. Here, omega is my frequency. The same frequency you can observe here. Now what I will do, keep this amplitude constant, okay, and omega I will make it change, okay. Change means what you are going to do. I'm going to vary this omega from 0 to maybe 100 or 100 hertz or something, okay. What does happen? This amplitude is B, A and B relation I need to establish. B is increasing somewhat like this. For omega 1 here, it is omega 2. I may have an omega 3 like this, multiple graphs like this. Okay. Now, I want to know this. I'm going to keep the constant, only omega I'm going to change. And due to that, this omega is creating a problem because it is increasing or decreasing the amplitude, output amplitude, which is dependent on omega, the A is constant. So for that purpose, what I can do is I can have an omega on one axis and ratio of output divided by input on other axis. Okay. So one thing you can observe in initial phase of this, I can have a constant, and later on I can increase the amplitude, will increase the amplitude and will get that stabilized. And what are this is due to very low frequencies. And what are this peak, you can get it because it is reached to certain resonance. After the resonance also you can observe. And this is what characteristics called as a frequency response of any curve. Why it happens? Basically, the system may have a stiffness, may have a mass, and it may have a damping interest. As in its natural frequency, that is omega n is equal to pi m or something. Okay? This frequency, your input is equal to omega is equal to omega n. There will be a resonance. Okay, and that resonance may be larger amplitude. Why resonance? You can observe one thing. This is my oscillation, input oscillation. This is my output oscillation. There is one curve all the time we plotted, that is omega versus phase. Phase means delay between my response, delay in the. If I take this two curves, if I plot onto one graph, that is, this is my input, my A. Another one, if I plot maybe an output curve, will not exactly match to this, but it will have something like this. And what are this delay? This delay is in phase between this. And as it is approval, this natural frequency, okay, as the frequency, input frequency to the system, this goes in 1 degree, means it is somewhere you will get a completely this kind of a curve, and that is what it is, phase or something. And in that case, initially you will observe your phase is constant, and then later on it will suddenly change and it will do when -180 degree or something. And that is going to cause at this point, sorry, this should be passing through this one. Okay. And this point, because your both amplitude, input and output amplitude are out of phase, and due to that, it is showing me a variation. Okay, and this is also a main important characteristics. And this particular response is called as a frequency response of your sensor. Frequency response. And how it will be used? My sensor should be operated or used in this range. My sensor should not be operated in this range. If my sensor is going to operate into this range, I may get in a very wrong result into this. I cannot predict what is going to happen. And this operating should be done this. This is one way of operation. Sensor operation should be in this range. Okay. So now we'll look at another part. This may be a first order response, second order response, so many things will be there into this. Okay. You can just go through these numericals, okay, and you will come to know how it is to be done. This is what on a graph you can observe. This is what on a frequency response. If I'm going to change this zeta, or I can say it is in a kind of an damping. If I am going to increase the damping, my curve will be different. And this particular point, I can get a resonance. This line and this line is the same frequency response. And this is typically represented in terms of a curve diagram, doing the same stuff, not any different stuff. The values may be in frequency response, we may call it as a magnification factor or something like this. So we can have a few examples. So sensitivity balance. Circuit is measured for a number of loads and gave the following results. So I done an experiment onto this. I have an balance. Okay. Okay, it is fixed here. And I want to know the displacement here. I put up on some sensor. Okay. Maybe a rectangular sensor, which is showing me an arrow, which is set to. I say this is my scale. One thing I observed here, I put the zero, my displacement is zero. As I'm going to increase the load, I got go on increasing the thus. Sensitivity means for one load, 1 kg load, I got a 10 mm displacement, 2 kg, 23 kg, I got 34 kg, 40 like this. Okay, so how can I determine this slope? It's in a simple. I can take this difference. Okay, this is my input and this is my output. Okay, and I can determine output. Now, out I can say which is delta in, and slope is nothing but sensitivity. Delta out, delta in, delta out will be 10, 10, 20 minus 10 is 10, 20 minus 10 will result into 2 into 1 minus 1. It will be 10 divided by 1, which is equal to output unit is mm. Input unit is that's why I comes into mm per kg or something. And this is what the way you can determine the sensitivity of any instrument. Okay? So we can classify these in different parts. It's not a very important point here to discuss the classification of analytics. Okay. Even secondary transducer, also digital, and so many things. You can divide it very problem into this. I think. Okay, we'll have some numericals. Okay. Suppose on a temperature, like having a range 20 degree to 120 degrees, linearly represented by standard current range. Here comes 40 milliamperes as for sensor. Okay. What will be the result at 6 to 6 degrees? Okay, okay. Now, so suppose on a temperature sense, that is x-axis. This is my minimum temperature is 20 degree, maximum temperature is 1 to 120 degree. Okay, 120 degrees Celsius. Then at this 20 degree point, getting an out as a 4 milliampere as in this, and for 120 degree, getting an output as in here 20 milliamperes. 4 ampere. The input is given. Okay, and it is represented. Here, the sensor is shown, it is a linearly represented. Okay, linearly represented means I can now join this line with this. Okay, linear connection between this point and this point within a straight line. Okay, so I want to now determine the equation for this. Okay, I have one condition here and another condition here. So to represent the equation, we use M plus C. In this M and C are two unknowns. That's what we should have two conditions for this. This is my one condition. This is my second conditions. So I can now have at temperature is 4 and temperature 120 degree, current is 20, like this condition. That's what I can now put here, that is yam into C or something. I0 is nothing. I can now write equation like I is equal to yam T into sorry. So here I want to find yam and I0. So for that purpose, 4 milliampere I substitute, which is equal to equations. Now I can simplify this and I can determine M and I0 values. Okay. Once I got this M value to somewhere, this value, okay, I got this M value, and I0 value, I got this much, 0.8 milliamperes. Ultimately, what you want to do is you want to determine the current, how much current it will be an output when I have a 66 degree. This is an equation. My equation will be an I. M is my 0.16 into T plus 0.8 is my equation. Now I can substitute 66 degree into this equation. I will get value, and that will come to be 11.6. If I put upon a 6.5 as a current, I can substitute here 0.65 milliampere as a current. And what will be the net temperature? I can do an inverse of this equation, and I will get a 35.6. So this is what the way you can now solve few numericals using this. Whenever you are doing any experimentation or any kind of a measurement, you may face such kind of a difficulty, and during that you can do this. So another example is accuracy base. Okay, so measured value. This term is used with maximum overall expected from device. Such that is such as measure useful measured value percentage. It is also represented in terms of a percentage, because whenever you are going to purchase any sensor, they give the accuracy in terms of a percentage of something, percentage of whatever the full scale reading, percentage of what. Here is I can measure it is 2 degrees Celsius plus or minus. Means I can assume if I have a temperature 50 degrees Celsius measured within a certain variable, the sensor is of plus minus 2 degree. I may have a temperature within what 48 degrees Celsius and 52 degrees Celsius. This is my accuracy rate. Okay. 0.5% of its full scale. in 5 voltage means I have inaccuracy or uncertainty into the measurement of this. How it has arrived to this 5 into 0.5 divided by 100 result into 0.025 volt. This is what in a minimum voltage accuracy I can get it. Okay, percentage of percentage. Okay, so 3% of its span will be something 19.1 psi, 20 psi. Well, that is what is on standard. Another one is actual reading. Actual reading is the reading the voltmeter having a 2 2.04. So within this range, it is. So now having a one more acceleration ground. So having a 20 degree, the measurement value is a 55 degree, and then that's how much error will be there. If accuracy of my sensor is of 0.5% of its full scale. Okay, full scale means what? This value, full scale, 250 degree. So now I can determine phase be 0.5%, 100 into what is my full scale? 250. Okay, which will result. Okay, this is a plus minus error, which is again multiply with your 55 degree or something. I can get an instead of multiplying, I can get plus minus 1.25 degrees Celsius. Means if I'm going measuring this temperature as 55 degree by my sensor, my minimum reading will be in a 53.75. That is 55 minus 1.25 and may have a 55 plus 1.25. 55 minus 5 comes to 53.75. Here it is in a 56.25 something. So my accurate reading will be within this range, but this is what a way you can represent for a full scale reading. If I say in a 0.75% of its span means what? I have to have 250 degree and here 0 degree is my. This is nothing but in a span. My temperature is varying from 20 degree. This I have now taken a difference to 50 minus 20 degree into 75. I got this much value, that is 1.7. Actual temperature measured minus 1.725, which is equal to 53.275 or something. And 55 1.725, which is resulting into 56.725 or something. Same is with a reading, percentage of the reading. Okay, percentage, 0.8% of the reading. This I may have some different accuracy and I can result into this value. That is what the way you can play with the sensor and its specifications. Okay, you have specifications. What your assignment will be one. You need to identify. Okay, this is my first assignment. Temperature sensors and its specifications from standard companies. Okay, and these specifications, based on the specifications, you need to amount of deviation in that particular sensor is that. Okay, that is accuracy to say. Now we'll have another stuff I want to determine. Uh, Transfer function. Transfer function is nothing but already we had in a discussion. This temperature sensor. Okay. I'm going to give an input, and this is my output. This is output. This is my input. Transfer function is not output divided by input is the ratio function, and that transfer function is given for input is degree Celsius. I'm getting this millivolt per degree Celsius. Okay. So in this case, the accuracy of plus minus 1%. Find possible range of the transfer function. Okay, transfer function range. How can I determine? Okay, transfer function. This transfer function gives me this much accuracy and 5 millivolt per day. 0 plus or minus 0.05 change means my transfer function may lie between 4.95 to 5.05 like this. Okay, that is what the way you can do it. Another example, this I got on the same, it is nothing but a connected to the net. Suppose my reading of my sensor is 27.5 millivolt. Okay, I want to know temperature, find the temperature that could provide the reading. Okay, because the transfer is 0.95 to 5.05. These are the two range. My temperature may lies between 5.56 to 5.45. So that is what the way you can determine it. Okay. Another example, that is force sensor measures the range 0 to 150 Newton. Resolution is 0.1% of its full scale. Full scale means this 150 I need to take it. Okay. Find the smallest change in the measure. You can have a 0.1 divided by 100 into my full scale reading is 150. I can have a 0.15 Newton as in change, measurable change in the force I can sense it. That is what. Okay. In some cases, resolution of measuring system is limited by sensitivity associated with your conditioning. And that is also another next part of it. Signal conditioning means maybe you have a Whetstone bridge or something. Maybe you have a potentiometer or divider comes under this. And that is also it is showing some kind of an error that also will be taken into account. Sensor has a transfer function 5 millivolt per degree Celsius and the required voltage resolution if signal conditioning, if temperature resolution is 0.2 degrees Celsius is required. What is the voltage results? Find required voltage resolution in the signal conditioning. If, see, here my sensor is, sorry, this is my temperature sensor. Okay. Taking that output is generating in terms of millivolt or something. This is further connected with my signal conditioning. This is a signal conditioning. Okay. and output is again converted into millivolt. I need to have a resolution of 0.2 degrees Celsius is required here at this point, not this point, because to sense it accurately, because you're going to have a multiple conversions. Transfer function is 5 millivolt per degree Celsius. Okay? You need to identify what is the voltage change in the signal condition. So obviously, I have to have a 0.2 degree change will result in voltage change. 5 into 1 milli change I should be able to detect it. Then I can say I can get a 0.2 degrees Celsius accuracy. That is what you can do the calculations. Okay. So similarly, you can just go through and a few of the numericals here in the PPT. Okay. I'll share the PPT to you people. Okay. So I will stop it for today's session. If you have any questions, you can ask me the questions now.